Okay guys, so we're going to start the next unit here. This is going to be types of equilibrium. So we're going to talk mostly about acid-base equilibrium and solubility. Just kind of, this is the idea of what you might see within your fields and what we kind of been building up to this entire course. So before we do any of that, let's go ahead and do a little bit of an equilibrium review. This is going to be a state of a chemical reaction in which the forward and reverse reactions proceed at the same rate. Okay? With that, we talked about the equilibrium constant, and that's just going to essentially be a numerical value obtained when the molar equilibrium concentrations are substituted into the equilibrium constant equation. And remember that that looks something like this. Kc is equal to products over reactants. Okay? And remember that these are our coefficients that we find from the balanced chemical equations. So remember, equilibrium is dependent upon stoichiometry. So as long as you can balance an equation correctly, you can solve for the equilibrium constant as long as you have those chemical concentrations. Okay? So now let's look at something new that we haven't looked at as of yet. I mean, kind of, but not really. And that's going to be acid-base equilibrium. So we talked about acids and bases in Unit 6. Okay, remember that? We talked about what is an acid, what is a base. Okay? And I remember I told you that we have certain acids that are going to completely dissociate and certain acids that are going to not just completely dissociate. The same thing with bases. So remember, those ones that didn't completely dissociate are called weak acids or weak bases. So when we're talking about acid-base equilibrium, that's just going to be equilibrium that involves a weak acid and /or a weak base. And we're going to talk about the and/or when we talk about buffers. And that's going to be where we see that we can have both a weak acid and a weak base involved in equilibrium. Okay? So, we have special names. Remember, we had the equilibrium constant that we talked about previously. Now we're going to have two different types of names for our special constants that are going to be found in acid-base equilibrium. The first one is going to be the acid dissociation constant. And this constant is going to be Ka. Okay? On the other hand, we're going to have the base dissociation constant. And that's going to be Kb. And clearly what we're talking about here, anytime we have a weak acid involved, which is what we're going to commonly more see within acid-base equilibrium, we're going to use Ka. If we have a base that's involved, we're going to use Kb. Okay? So, one other thing we need to talk about before we get into solving for Ka and Kb, because that's kind of the whole point of equilibrium for acids and bases, we need to talk about pH. And I'm sure you've heard of this before. At some point or another, you've probably had to check the pH of, the urine for a dog or the urine for cats or something along those lines. I'm sure you've had to deal with pH at some point. So we're going to look at how we calculate pH given a molar concentration of either our hydrogen ions, or if we have the case, we're going to solve for a POH and then solve for pH if we have the hydroxide ions, okay? So when we're going to talk about all of these, we're going to have to remember that all of our hydrogen ion concentration is going to be very, very small, okay? So because of this, because the molar concentration of our hydrogen ions is very small, the concentration of our hydrogen ions is expressed as a pH. That's what we call it. And for this, unless I tell you otherwise, you're going to round to 1 decimal place. That's just going to be your rule of thumb. Okay, so we're not worried about significant figures here. And the idea to find pH, it's just going to be the negative log of your hydrogen ion concentration. So that's how you find the pH. Okay? Pretty simple, pretty easy. You are going to need your scientific calculator. If you don't have a scientific calculator, you can always look one up online. I know that there are a couple that are available there. Normally I just tell you, hey, I can give you one. Unfortunately, with us doing this remotely, I can't give you one, so here we are. But what I can tell you is you can find the, a TI-84 similar or, a scientific calculator app online. Okay? Okay. Next one. So when we talk about the POH, we've already talked about what we kind of make for our concentration for our hydrogen ions, but in a lot of cases you're going to be dealing with the hydroxide ion because that's what's going to be used for a base. So therefore, we're also going to see a very small concentration of that as well. So because the molar concentration of our hydroxide ion is very small, the hydroxide ion concentration is expressed as a POH. Okay? So here we're going to do the same thing. Remember, we're going to round to 1 decimal place. Unless I tell you otherwise. So how do you find the POH? Well, if you find the pH by taking the negative log of the hydrogen ion concentration, it's going to be the same thing, except instead of the hydrogen ion concentration, I'm going to use my hydroxide ion concentration. So it's going to be the negative log of the hydroxide ion concentration. And then, in order for us to be able to use the POH to find our pH, we're going to have our pH plus our POH. This should equal 14.0. Okay, and that's the end of our hydroxide, or that's the end of our pH scale. Okay? Okay, so let's do some practice with this. First one's going to be here. It says find the pH of a solution that has the hydrogen ion concentration of 3.25 times 10 to the negative 3. So all you have to do is put pH is equal to the negative log of 3.25 times 10 to the negative 3. Okay? And then we're just going to put that into our calculator. So, you see this log button here. So all I'm going to do, see everybody see this log button? Okay, so all I'm going to do is I'm going to put my negative sign, negative, log, and then I'm going to put in my number. Okay, so I'm going to get some number that goes off for forever. But remember what I told you, unless I tell you otherwise, you're going to round to the first decimal place. So the pH is going to be 2.5. Make sense? Should seem pretty easy for this. Okay? Next one, we've got a pOH that we're looking for here. But we are given the hydrogen hydroxide ion concentration of 4.225 times 10 to the negative 6. So again, I'm just going to write the pOH is the negative log of what my hydrogen or hydroxide ion concentration is. So that's 4.25 times 10 to the negative 6. Okay? Our pOH is going to equal, so again, I'm just going to do my negative sign. Everybody sees that? Log 4.25 second E to the negative 6. Okay? So again, I'm getting this super long number, and most of the time when you do these logs, you're going to get a super long number. But I told you we only round off to the first decimal place, so 5.4. That's my pOH. Now, this one's probably going to be the hardest one you'll see, and I still think it's pretty simple. You're going to look for finding the pH of a solution that has a hydroxide ion concentration of 2.25 times 10 to the negative 2. So what you're going to do for that, the first thing you have to do, we can't relate the hydroxide ion concentration with our hydrogen ion concentration. We can't do that directly. We have to put it into this pOH or the pH because that's what our relation is. Okay? We don't really say our hydroxide ion concentration. Most of the time we're going to talk about it as a pH. So we need to use this formula right here. And in order to be able to use this formula, I need to find my pOH. So that's the first thing I'm going to do. So I'm going to go ahead and put my pOH is equal to the negative log of what my hydroxide ion concentration is, 2.25 times 10 to the negative 2. Okay, so putting that in, we're going to get negative log of 2.25 times 10 to the negative 2. Okay, so I get 1.6. Does everybody see that? Then, to find my pH, I just take 14.0 minus my pOH, which equals 14.0 minus 1.6. And then I just put that into my calculator. Hopefully everybody can see that. 12.4. So my pH of this solution is going to be 12.4. Does this make, hopefully this makes sense to everybody. I think this is pretty simple. Hopefully this is going to be the easy part of our entire situation. So let's go ahead and go to the next step. Okay, so now we got enough information that I can go ahead and determine my acid dissociation constant. And that's going to be Ka, okay? And again, this is just the equilibrium constant. For the ionization of an acid. Okay, so here we've got this information here. This would be my typical acid equation. A is going to be my, ion for my acid, and obviously we have our hydrogen ions. Okay, so if I have this situation, they're all aqueous, so that means that they're all included in my equilibrium constant equation, or my acid dissociation constant equation. Okay, so I'm going to write Ka, because it's special, and then I'm going to put my products over my reactants. So I have H plus 1, concentration of H plus 1, concentration of A minus 1. And since these both only have 1 is there as the coefficient, and most of ours that we're going to be dealing with, actually I restate that. All of the ones that I'll give you as examples, because I'm not going into how, phosphoric acid and sulfuric acid, how they dissociate. We're not going to be concerned with that. So therefore, we're just going to be concerned with anything that has a +1 and a -1 charge. So therefore, they have 1 as their constant, so I don't have to write anything for that. Okay, and then I'm going to put it all over the concentration for HA, okay, or my acid. Okay, so this is how I write my Ka, my acid dissociation and constant equation. Okay, so let's look at how we solve for our Ka. And there's some steps we have to go through. It's kind of simple, similar to what we're going to do, what we did for solving for Kc, okay? So the first step, we're going to write the acid dissociation constant equation. Then we're going to make an ice table, and everybody remember what an ice table is. Initial, change, equilibrium. Okay, then we're going to plug in all values that we can into the ice table. We're going to determine the equilibrium concentration of H+1 from pH if we're given pH. And that'll be at our equilibrium pH. So whatever our concentration is, whatever our pH is at equilibrium, most of the time that'll be told to you. Okay? Then you're going to find the change in concentration. For each product and reactant. Using that change, you'll be able to find the equilibrium concentrations of all of your products and reactants. Okay, and then you're going to use these equilibrium concentrations to find you're going to find Ka. Okay, so let's go ahead and start this whole situation with our first example. We'll start that in the next video. All right, well, actually, we'll continue. I apologize. We're going to continue. Okay. So this is going to be a weak acid. This is actually formic acid. Okay. Some may have heard of it before. It is found in our body. Okay. So formic acid. So when a 1.0 molar solution of formic acid is prepared, the pH is found to be 2.38 at 25 degrees C. What is the acid dissociation constant Ka? So the first thing I'm going to do is write my acid dissociation constant equation, okay, which is going to be products over reactants. So the concentration of H+1 and times the concentration of COOH -1 all over formic acid. Okay. Next step is to make my ice table. I've already done that for you. And we're going to plug in all the values into the ice table. So the first thing, we're going to have our initial concentration of 0.10 and then 0 and 0 because it hasn't done any dissociation when we initially make this solution. Okay? Since equilibrium per our principles of Le Chatelier's is going to go towards the right, it's going to be -x here, +x, and +x. Now, I'm not going to finish filling in my equilibrium concentrations because I've been given a pH. So I can determine my equilibrium concentration for H+ by doing essentially the reverse of my pH equation. So remember, what was my pH equation? pH is equal to the negative log of the H+1 hydrogen ion concentration. Okay, so how do I solve for this? The first thing that's kind of easy, right? I can go ahead and maybe why don't I put in my pH? 2.38 is going to equal the negative log of H plus 1. Okay, so the first thing I can do is I can take this and divide by a negative 1. Okay, so if I divide by a negative 1, I'm just going to negate both sides, and this will give me 2.38 is equal to the log, negative 2.38 is equal to the log of H plus 1. Okay, now if I'm going to do the opposite of log, I'm going to take it 10. So this is kind of how you can see this on your calculator here. Most of the calculators are going to have log and then 10x. You might also see ln and e to the x. This is important if you were going to do a little bit more more sophistication, especially with kinetics, which we are not covering in this course, so we're not really concerned too much with ln. But remember, whenever we're dealing with log, we're doing base 10. Okay? So I'm just going to take everything 10 to the blank, 10 to the blank. So my hydrogen plus 1 ion concentration is going to equal 10 to the negative 2.38. Okay? So if I do that, I say second 10, and then I put in negative 2.38, should give me some number. Okay? So my hydrogen ion concentration at equilibrium is going to be 0.00417 molar. Okay, so this is what I can put into my table here. That's going to be 0.00417. Okay, and if this is equal to just x, then x equals 0.00417. Okay, does everybody see that? So the next step, I can just fill that in for my concentration here. And then to solve for my equilibrium concentration here, I would take 0.10 minus x, and my x is this value here. Okay, so remember, x is equal to 0.00417. Okay? So if I solve for that, I need to find my concentration at equilibrium for my formic acid, because that is what's going to help me determine my acid dissociation constant. Okay? So, we're going to go ahead and do that. We're going to put in for x 0.00417. Okay. So go ahead and put that into your calculator. Okay. So this number here, that's what we're going to get. But isn't that really close to what we just had with 0.10? So if we do that, we say it's just going to remain the same. So let's look at if we put in this number and we put in this number and see the difference between our equilibrium constants. Okay. So for the first one, I'm going to use this number here. So again, I'm going to put my concentration for my hydrogen ions, my concentration for my COOH ion, all over my formic acid concentration. Okay? So, this will give us, when we put it into our calculator, okay? So, which would equal 1.8 times 10 to the negative 4th. Okay? Now let's look at if we keep this the same. Okay? So again, we're going to fill in the same way we did on the top. The only thing we're changing is what we're filling in on the bottom. Okay. Okay, so we've got 1.8 times 10 to the negative fourth and 1.7 times 10 to the negative fourth. That difference, if you think about it, look how far out we are from our decimal point. That means that it's a very, very, very small number difference. So this is what we call a negligible difference. And therefore, I can just use this number here, whatever my concentration is initially, as my equilibrium concentration. Does this make sense for everybody? I hope it does. The whole point behind this whole idea is that the concentration of your hydrogen ions is always going to be very, very small. And because it's very, very small, whatever that concentration is, that also means that the dissociation concentration for whatever your cation or your anion is also going to be very, very small. So therefore, whatever we take out of this large number that we started with compared to these numbers is going to be very, very small. Again, I've said this very, very small a couple times. So therefore, I can almost say that that's a negligible difference between this number and this number. And therefore, we'll have a negligible difference between my Ka with this number versus this number. And oftentimes, it'll end up being the same. So for that reason, we just use our initial concentration from here on out. Okay? Okay.